Space. I want to talk about space. So welcome back to the Daily Dean. This time it's astronomy instead of like motivational stuff. So basically the Doppler Effect specifically. Now, what is the Doppler Effect? Well, it's a topic relating to waves. It's like sound waves, right? And like light waves. So I'll go back to sound waves. When you're hearing something, what you're hearing are vibrations in the air, right? If I snap my fingers, the vibrations of my fingers, clapping down like that, gets vibrated into my eardrum, and then I process that as sound, okay? Now, you can change the sound of something by compressing the wavelengths, right? And wavelengths are measured by, once again, you have to imagine it like a wave, how close together the waves are, right? So then, here's a really long example of a wave, right? And then here's a really short example of a wave. You can tell that it's more compressed if you're like visualizing it along with me as I'm, drawing it in midair. And that changes the way that sound is heard in your eardrum. So, what does that have to do with the Doppler effect? Well, the Doppler effect is about like moving sound sources, right? If I snap my fingers once, the sound just travels like that, right? It just goes straight to my eardrum, vibrates, boom, I hear it. But if you're standing right here and a train runs past you and it's whistling, like, toot toot or whatever sound trains make, it'll go from, it'll go closer to you and generate a higher pitch going, right? That was my best attempt at a train sound. And you can imagine that with an ambulance as well. When you hear it coming closer to you, it gets higher pitched, right? It goes, and then gets lower pitched. Now, why does that happen? You could say, oh, it's because the position of it is moving. But what's actually happening is the sound waves from the whistle gets compressed together as the source is moving towards you, right? And as the source is moving away from you, it extends the sound, right? So if this train was totally stationary, you could stand here, hear the same pitch, or stand here, or stand here, etc., whatever. But because it's moving, that changes how the sound waves enter your eardrum. Now, okay, that's a pretty practical example. Well, what's an impractical example that you might never experience, but is really cool to think about? Light. Okay? Light also travels in waves. And when you see something, the difference in that wavelength changes what you see, right? So if you see the color red, it's at a specific wavelength that the light travels in, okay? But if you see the color blue, it's a different wavelength. Something that travels in slightly shorter wavelengths, okay? Now that's important to differentiate. Red wavelengths, the stuff that you see that hits your eyeballs, those are longer than the bluer wavelengths, like this, right? The bluer wavelengths are shorter in comparison to the longer wavelengths of red, okay? So, what if a light source is moving and you're seeing that light source hitting your eyeballs, okay? Basically, you'll see the color change depending on how fast it's moving towards or away from you. Now, what does that really look like? Well, imagine a star is emitting like yellow light, the current wavelength that we can see. It's just beaming towards us, okay? But if the star is moving away from us, the wavelengths of the light get stretched out, way stretched out. And that in turn means that it becomes more red shifted. Because as I said, red wavelengths are longer. If the light source is emitting light, but the light is being stretched out, it makes it appear more red, right? And then if it's moving towards you, it becomes more blue shifted because the light gets compressed, making it look more blue, right? So, that's kind of crazy, right? Imagine if, I know I'm saying right a lot, but imagine my little blue pencil bag was emitting light, and the light it was emitting was blue. if I chucked it away from us, way farther out, it would appear more purple because the blue light gets redshifted to the red spectrum. And you can apply that to, other stuff, but obviously I can't chuck something fast enough or hard enough in order to make it, red shift or blue shift. But the idea that this happens is crazy. Now somebody told me that's actually that's actually a piece of evidence to how we know the universe is expanding. The universe is expanding, as many of us may already be aware of, and we can tell why, and we can tell how, or we can tell it is because the universe, the galaxies that are receding away from us in every direction is red shifted. Once again, red shifting means that it's moving away from you. And if every galaxy in the universe is red shifted, then that indicates, the universe is expanding around us. Now, I saw this from a Vsauce video. The universe expands in every single direction at once, okay? And if the universe is expanding in every single direction, that means that the center of the universe can change from the perspective of the expansion, right? For example, my finger right here is totally stationary if I hold it as still as possible. But because everything in the universe is receding away from it, including, the galaxy and the sun, that means that my finger becomes the center of the universe just by thinking about it. Because once again, if everything is receding from everything else, that makes the center relative. So you are the center of the universe. I am the center of the universe. Everything around us is the center of the universe, depending on how you look at it. So I know that was a lot to take in. That was kind of a rant on astronomy and cool stuff. But I hope you enjoy that. I personally enjoy it. Maybe you look at cool stuff like Vsauce. They're a great YouTube channel. And maybe consider taking an astronomy class. I think that's also interesting. But that's all I gotta say, so thank you.